So here goes. So this is, now we are coming towards the last part of vectors, and another couple of weeks and we should be done with vectors. So today's lecture we will be discussing a couple of things. One is we will be discussing about something called direction cosines. For three-dimensional component representation. And then we will be discussing about, the second thing we will be discussing in the class today is about scalar product. Okay. Where you should not think of this like multiplication. Okay. The product operation for vectors is very different than the multiplication of numbers, because multiplication that we know till date, that 2 into 5 is 10, something like that, or 5 into 0.2 is 1 or something like that. That applies to scalar quantities, or that applies to pure numbers. But here, since vectors have direction, so we don't really talk about vector multiplication. Yes, we do talk about multiplication of a vector by a scalar that you've seen earlier. But if you are operating on two vectors, vector A and B, then there's no such thing as multiplication of vector A with vector B. You can multiply vector A with a number like 0.5 or with a scalar quantity like f is equal to ma. But we cannot really multiply two vectors with themselves. Instead, we have two types of product operations. So one of them is called scalar product, or it is also referred to as the dot product. And another one is called vector product, or it is referred to as cross product. And we will understand both of these in detail. So we'll start with the scalar product in today. But anyhow, let's start with the first thing that I just told you about, which is going to be about direction cosines. So first up, direction cosines. Okay. So if we have a three-dimensional system, a normal three-dimensional XYZ system that we talked about, where remember that the XYZ coordinates axes are mutually perpendicular, and they're mutually perpendicular and drawn according to the right-handed system. So this is a 90-degree angle, this is a 90-degree angle. So we have three mutually perpendicular planes, right? The XY plane, which kind of in the diagram should look vertical to you over here. The YZ plane, which is this plane over here, this should also look vertical, this should also look vertical. Whereas the XZ plane in my diagram looks like the horizontal flow, that kind of situation. So if we have a vector in this situation, or a vector which is drawn with respect to this coordinate frame, okay, and it's an arbitrary vector, so it's not lying in any of the planes. In my diagram, it might kind of look as if it's in the XY plane, but just try to imagine it's outside the XY plane. So it's just an arbitrary vector, which is from O to some point B like this. So if this vector is denoted in component form as some X component into I cap plus some Y component into J cap plus some Z component into K cap. Okay. Then we define something called direction cosines. So first of all, we say that the angle with respect to the x-axis, we denote it with the symbol alpha. The angle with respect to the y-axis, we denote it with the symbol beta. And the angle with respect to the z-axis, we denote it with the symbol gamma. So alpha, beta, and gamma being the angles made by the vector E with respect to the positive x-axis, the positive y-axis, and the positive z-axis, respectively. So if alpha, beta, and gamma are respectively those angles, then the quantities cos alpha, okay, cos beta, and cos gamma are called they are defined as what we call the direction cosines. Collectively, these three quantities, cos alpha, cos beta, and cos gamma, are given a collective name, and they are called the direction cosines. Still have a couple of people joining. So it's not a question of why only cosine. It's a question of we define direction cosine. We can find sine and tan also, it's not a problem. But the thing is, we define the quantity in terms of cosine, and they are called the direction cosine. Okay. Now the most important thing, the formula for them, where cos alpha is given by the simple formula Ex upon magnitude of B. Cos beta is given by the simple formula Ey upon magnitude of vector. And cos gamma is given by the formula Ez upon magnitude of. This is the formula that is used to calculate the angle with respect to the axis. That we know the formula for the direction cosine, and then we can apply the cos inverse concept of it and just find out the angle. So where of course you know that the mod A we have discussed earlier for any vector, it is defined as root of Ex square plus Ey square plus. So first of all, I'm just minimizing this little bit for you to understand the whole concept here. This is how we define direction cosines. We define the angles made by the given vector with respect to the x, y, and z axis, as we generally denote them with alpha, beta, and gamma. Okay. So cos of alpha is defined as a direction cosine. Cos of beta is defined as another direction cosine. And cos of gamma is defined as another direction cosine with respect to the z-axis. Cos beta is with respect to y-axis, and cos alpha is with respect to x-axis. So these direction cosines collectively are cos alpha, cos beta, and cos gamma. And formula-wise, they work out to be cos alpha works out to be x component divided by mod of the vector. Cos beta works out to be y component divided by mod of the vector. And so I can see from a lot of the questions, the messages that you are sending, particularly I think Piyush and all, people are worried about why only cos and all that. So I will just ask you Piyush at this stage not to worry about why cos. Okay. Yes, if there's a way to find out cos alpha, there must be a way to find out cos sine alpha also and tan alpha also. Okay. It's not that we are taking only this in consideration. It's like, if I only, if I'm saying that you should have protein in your food, it doesn't mean that I'm saying why should you take only protein. You should also have carbohydrates. I'm not saying that just because you have protein, don't have carbohydrates. But I'm just asking you that you should have protein in your food. It's one component of your food. It's one important ingredient of your food. So just like that, it's not a question of why do I consider cos alpha? Why don't I consider sine alpha? It's a question of how I calculate cos alpha. That is the important question. So instead of repeating your question again and again, I would advise you to concentrate on what we are learning over here is how do we calculate cos alpha, cos beta, and cos gamma? We calculate it from these formulas. That cos alpha is Ex upon mod A, cos beta is Ey upon mod, and like that. And to answer your question, no, vector does not have a solid angle. A solid angle is a quantity which belongs to a surface or a three-dimensional body. Okay, so solid angle is something we will discuss about later. See, plane angle, or what we just normally in everyday language we call angle, that is a quantity which is related to two lines. Okay, two lines, unless they are parallel to each other, always they intersect in such a way that there is some angle between them. So if arbitrarily in 3D, I just draw two lines. One line is like this, and unless the other line is parallel to it, it might be intersecting at some point. And if they're intersecting at some particular point, then the angle made between these two, that is called the angle between the two lines. So if you denote the angle between two lines as theta, then obviously the other angle, which is 180 minus theta, is also an angle. So if I say the angle between two lines is 45 degrees, it's as good as saying the angle between the two lines is also 135 degrees. Okay? So that's about two lines. But the moment I talk about two vectors, remember, or two lines which have direction, it becomes more specific. Why it becomes more specific? Because you are considering the vector arrows. So one vector is along this direction, so its arrow is pointing like this, and the other vector is along this direction, so its arrow is pointing like this. Then we will always consider the angle between them as the smaller of the two angles between the arrows. You learned this in vector addition and things like this. This will be considered as the angle between the two vectors, because to change from the direction of A to the direction of B, you have to rotate by how much? You have to rotate by theta. You rotate by 360 minus theta. You rotate by theta. So just like that over here, I have now the particular vector B, and instead of another vector B, I'm looking at the positive x-axis. If this is my positive x-axis, for example, then this angle here will become alpha. if this is my positive y-axis, let us say, then this angle will become my beta. And somewhere else, if I have my positive z-axis, then the angle made that will become my gamma. So there's no complication about this, that why this angle, why that angle, and all that. We are not really right now exploring the SF2. We are just saying that SF, this is what we are defining. I'm not saying why don't I define the angle made with the negative x-axis, why I'm defining only with the positive x-axis, or why I'm not saying sine alpha, why I'm saying cos alpha instead. It's not a question of that. Later I can find out sine alpha. That's not the problem. The thing is that I want to see how will I calculate the angle made with the x-axis, how will I calculate the angle made with the positive y-axis, and how will I calculate the angle made with the positive z-axis. So that will come from this set of definitions, that the direction cosines are given by these components. So without worrying about other things over here, let us learn to apply the concept of this one. Okay? And let's see that, for example, for a given vector, how we can easily now find out the angles made by the x, y, z axis. So for example, so this is where it becomes important to understand the application part. So for example, if I have a vector like this now, E, which is having magnitude of, which is having components root 2 I cap minus root 2 j cap plus 2 q cap. Okay. Now I ask you that first of all, find the magnitude of it, which all of you know of it. So that's very simple. Then secondly, find the direction cosines. Okay. Cos alpha, cos beta, and cos gamma. I want to find out all the three direction cosines. And third, from that, I want to calculate alpha, beta, and gamma. Yes, Dhruv, that's correct. Where the meaning is standard, where we understand that alpha is the angle made by vector E and the positive x-axis. Similarly, beta is the angle made between this and the positive y-axis. And similarly for gamma, the positive z-axis. Right? Okay. It's just a matter of substituting in the formula now. Yes, very good, Aditya. Your answer is correct. Only what you've given for cos beta, it actually applies to beta. Very good, Dhruv. Your answer is correct. Yes, Smith, your answer is correct. Yes, Piyush, correct. So let's check this out. So you can see that given the vector E was square root of 2 I cap minus square root of 2 j cap plus 2 times k cap. So the first formula I will apply is for magnitude of the vector. So for mod of the vector, I can see that it is root of ax square, so that is root 2 whole square plus minus root 2 whole square plus 2 square. So it is square root of 2 plus 2 plus 4. So that is square root of 8. That is 2. So the magnitude of the vector is 2. So now you can see, so that's the first one. Now about the direction cosines, you can see that cos alpha, according to formula, is ax upon mod. So that is how much over here, root 2 divided by 2 root 2 or half. So that means alpha is how much? It is 60 degrees. Similarly, cos beta. So not only I've got the direction cosine, I've also got the value of that angle. So the third part is also that. So cos beta is simply ay by a, and that is nothing but minus root 2 in this case, divided by 2 root 2. So it is minus half. So if cos beta is minus half, that means in this case beta is an obtuse angle and it is 120 degrees. And similarly, cos gamma is Ez by A. So that is 2 divided by 2. So it is so gamma is becoming 45 degrees. So that means when we visualize this vector, it is such a vector that is making an angle of 60 degrees with respect to the positive x-axis. 120 degrees with respect to the positive y-axis. And 45 degrees with respect to positive z-axis. So pretty simple, nothing difficult. So it's all formula application. But this way, there's nothing much to think about. You just apply the formula here. Yes, Yashmin. No, because see here, Yashmin, we are talking about this thing. Or rather, Ranak, to answer your question, why we should write it as 60 degrees and not as 300 degrees is because we are talking about the angle between two vectors actually. The positive x direction also represents a direction. So in that sense, it is like a vector. It's a vector along the positive x direction, and there's a vector e. So between two vectors, if an angle, if one vector e is like this, and your x-axis over here is like this, your positive x-axis is in this direction. If this angle is 60, you'll always report alpha as 60. It won't make sense to report alpha as 360. I mean 300. It's just like this. So what we understand through this example is that either your direction cosine can be a positive quantity, in which case the angle is acute, or it can be a negative quantity, in which case the angle is obtuse. Note that if cos alpha is a positive quantity, that will always mean that alpha is an acute angle. Here it is not with respect to the xy system. So it is not a, it's not a trigo in 4 quadrant concept. It is just the angle between an axis and a particular vector. Okay. Similarly, if cos alpha is 0, that means alpha is 90 degrees. And if cos alpha happens to be negative, then it just means that alpha is obtuse. That's all it means. So let's look at another example, another couple of examples which make this very interesting. Okay. So find the angles alpha, beta, and gamma for the following vectors. This time we'll see something interesting. We will see a vector which actually lies only in the xy plane. 3i cap plus 4j cap. But let's apply the formula anyway and see what we get over here. Similarly, let's take the case of a vector which is lying, say, like this. It is 3i cap plus 4j cap. 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 So it is minus I cap plus root 3 k cap. So this is a vector which is lying in the xz plane, and the first one A is a vector which is lying in the xy plane. So let's see what we get for alpha, beta, and gamma in this case. There's something interesting that we'll understand in terms of properties of this also. Okay, so that's good, right? No, Sarvesh, to answer your question, here alpha plus beta will not be 90 because it's 3-dimensional. Okay, that happens only in a 2-dimensional plane. That alpha plus beta is 90 only if gamma is equal to 90 degrees, or rather gamma is 0. Just a moment, I will share the board again. Yes, cos alpha is 3/5. So for the first one, you should get alpha as cos inverse 3/5. So that is how much? 53 degrees. You should get beta as cos inverse 4/5. So that should come out to be 37 degrees. And you should get gamma as cos inverse 0. So gamma is 90 degrees. Now, if you really think about it, it makes sense, because why it makes sense is to understand that the given vector, which is 3 cap plus 4 cap, this vector, first of all, it lies in the xy plane. So anything that lies in the xy plane, naturally it should be perpendicular to the z-axis by definition. You can see that's happening. And in the xy plane, it is lying such that if you just draw your xy plane, you understand that the vector is lying like this. Because this is 3 and this is 4. So naturally, this angle is 37, is 53. That is your alpha. So naturally, your beta, which is the angle made with the y-axis, will have to become 37. So that's why this is 37, whereas this one is 53. So anyway, how did I get this? I got this by just a formula. So the method here was this. That I understood that for the vector E, the x component was plus 3. The y component was plus 4. And the z component was 0. So that first of all meant that mod A was 5. And then from that I got that cos alpha is 3/5. Cos beta is 4/5. And cos gamma is 0. And then I just use my common knowledge of trigonometry. Now notice that so far I haven't given you a proof of this, and I will be giving you proof very soon. Okay. In fact, interestingly, it is something that we learn in dot product, the next part of today's lecture, which will help us understand the proof of these direction cosine formula. Raj, you do know that cos of 53 is 3/5 times. 3, 4, 5 triangle, Raj, let me remind you, we've discussed a number of times. Okay, so these 45 degrees, etc. You are supposed to remember. There is no info here. Just know the simple idea that if cos alpha is 3/5, that means alpha must be 53 degrees. Just like you know that if tan theta is 1, theta must be 45 degrees. So why to use any complicated thing like And I don't want to complicate things by using inverse functions and all that. It's not required. I'm not doing any operation of inverse trigonometric functions or anything. I'm just using very simple language here. कि अगर cos alpha का value 3/5 है, तो alpha कितना है? So I know the reverse of this. I know cos 53 is 3/5. So naturally alpha is how much? 53 degrees. There's no inverse trigonometric operation involved with this. Keep things as simple as you can. There's no need to unnecessarily add complications. So like that, let's come to the second part. So the vector b was given to you as this time minus root 3 I cap plus k cap. So you notice something interesting. This vector is actually lying in the xz plane. Okay. You can see that the x component is minus root 3. The y component is in fact 0. And the z component is positive or negative. So that also means that the magnitude of b is how much? It is root of 3 plus 0 plus 1. That is 2. So now we know from this that cos alpha is bx upon b. So that is nothing but minus of root 3 by b. So again, I don't need to apply any inverse trigonometry on that. I can just see that it's a negative quantity, so it's obtuse. Now मुझे पता है that cos of 30 कितना होता है? root 3 by 2 होता है. तो cos of कितना minus root 3 by 2 होगा? Sorry, 2 by 2. So alpha कितना हो जाएगा? 180 minus 30 or 150. Simple. This I know from trigonometry in second quadrant. So I'm not using inverse trigonometry. I'm just using very simple thing that in second quadrant, I know that cos of 180 minus theta minus cos. Just I'm using that. So since I know that cos of 30 is root 3 by 2, so I know that cos of 150 has to be minus root 3 by 2. So I'm not doing any inverse trigonometric operation over here. Okay, all that you learn in maths, and it's very good to know all that. Okay, but all I'm doing here is using simple trigonometric equations, not inverse trigonometric equations. So cos of 1, in fact, I'm using simple formula, not even trigonometric equations. I'm just using the formula for second quadrant. So इतना कुछ आपको टफ सोचने की जरूरत ही नहीं है. Just as long as you're clear with first and second quadrant formula. Similarly, you can see cos theta is 0. So obviously that means beta is how much? It is 90. So this is 150. This is 90. And cos gamma is dz by b, which is over here becoming how much? Half. That means gamma is how much? It is 60. So these are the values of alpha. Correct, yes, we do that. You got the right answer. Same as I put up over here. You just complete the steps of this is dy value, so that dy is 0. So now you can understand why this is happening, because the vector b, which is minus root 3 I cap plus k cap, it's actually, this lies in the xz plane. How I know it lies in the xz plane? Because its y component is 0. Therefore, because it lies in the xz plane, therefore it has to be perpendicular to the y-axis this time. In fact, if we draw a diagram of the xz plane like this, that this is my x-axis and this is my z-axis. I'm looking into the xz plane. So how this vector will look in this diagram now? This vector v will look like this. It will be having a negative x component and a positive z component. Could it be like this is my vector v, it is having an x component which is minus and a y and a z component which is positive or 1. So in this diagram, basically I'm looking into the xz plane. So it's like, normally when I draw an xyz axis like this, it's like this. Now imagine your line of sight here is like this. This is how you're looking. This is your line of sight. If you look straight into the xz plane, the diagram will look like this. In this diagram, y-axis is coming out of the plane towards you. Okay, so hope you've understood about the significance of significance and also the general understanding of direction. Okay, now one very important property of direction cosine we see is this next one. And that important property is this, that cos square of alpha plus cos square beta plus cos square gamma has to be unique. This is like a theorem, and I can give you the proof of this theorem just now. So in words, we can say that the sum of the squares of the direction cosines of a vector equals 0. Now the reason why this happens is very simple. This is since you can see that cos alpha is ax upon u, cos beta is, yes, just apply the formula, that is correct, and cos gamma is az upon u. Therefore, left hand side of the equation, which is cos square alpha plus cos square beta plus cos square gamma, is nothing but ax square plus ay square plus az square, and all of them have a common denominator. So when you take LCM, you see that it is just ultimately unity. That is equal to right hand side. Okay, so this is one important little property that you should keep in mind about the direction cosines. And if you just see the last few questions we did, if for example, in one question we had cos alpha as 1 by root 2, cos beta as 1 by 2. minus 1 by 2 and cos gamma as 1 by root 2. You can see that this property applies over here. Another example we did, we had cos alpha as 3 by 5, cos beta as 4 by 5, and cos gamma was 0. So again, you can see this property applies. Yes, Piyush, what is the doubt now? Let me understand. Yeah, Piyush, this is the property of direction cosines that I'm explaining over here. That it's actually given over here. It's very simple. Cos square alpha plus cos square beta plus cos square gamma equals to 1. This is an identity. This is the statement of the identity that sum of squares of the direction cosine of the vector always equals to unity. And this is the proof of this. Because cos alpha is defined as ax by a, cos beta is defined as ay by a. So if you just see the left hand side of the identity, it is nothing but ax square by a square plus a by square by a square plus az square by a square. By a is nothing but magnitude of the vector. If you expand this further, you understand why it becomes unity. Yes. So Raj, what you are saying is correct. Now suppose the vector is two-dimensional, like in this example, cos gamma is 0. That means actually gamma is 90. So it's lying in the xy plane. तो वहाँ पे क्या हो जाएगा? Cos square alpha plus cos square beta unity हो जाएगा. Similarly, the third vector, it was lying. Remember, the third vector was something like this. Cos alpha was minus root 3 by 2. Cos beta was 0. And cos gamma was the non-zero quantity. It was half. So for this vector, what will happen? You have cos square alpha plus cos square gamma will be unity because cos beta is 0. So, if the vector can be reduced to two dimensions, in the yz plane, this cos alpha factor will be 0 because alpha will be 90. Okay. But in general, I'm saying, which the identity which is applicable to all vectors, irrespective of whether they lie in a particular plane or they are three-dimensional. That is this one, that cos square alpha plus cos square beta plus cos square gamma is unity. Also 90. So that happens in formula that you are saying that so gamma is 90 degrees. Okay. So if anybody is experiencing any internet issues, I think 2 or 3 people were getting logged in, logged out. Just to remind you, I am recording the lecture, so you will get the video recording with perfect. So yeah, if we have that formula, that mod is root of x square plus ay square plus az square, from that formula only we get the derivation of this theorem. It's not the other way around, that this theorem is yeah. So just reminding students that if you are having any lag in the voice, etc., because of internet connectivity issues, I will make the video available immediately after the lecture. You can also try logging out and re-logging in once. That way, your connection might improve. The data transfer might improve. But if you're purposely logging out and you want to re-log in, better if you just drop me a message. But then I'll make sure I'll be alert on the waiting room, because we'll appear in the waiting room and so that you don't have to wait. Okay, so this is about direction cosines. Okay. Now we move on to the second part. Now, remember that I haven't given you the formula of direction cosine. So why is cos alpha equal to ax upon mod a. Why is cos? So I'll be coming to the proof by the end of today's lecture. Come again, what was the issue? Okay. Are you having a glitched video or something? Hope it is clear now. I will just stop the share once and make sure the video is clear. Yeah, there does seem to be a bit of lag in the video. Okay. So thanks for informing me. So these glitches are happening because of internet connectivity issues, people. Okay. So don't worry, the video recording will be fine. Yeah. Okay, people, just take a people just take a 2-minute break. I will readjust my network adapter. Okay, so I think things are more or less clear now. Right, so let's come to the second part of our lecture today, which is the very important operation called scalar or dot product. So it's a type of vector operation which gives us a scalar quantity. That's why it is called scalar product. So this is defined by this. By definition, first of all, this is the symbol that we use for scalar product. So this symbol is read as scalar product of vectors A and B. Or in short form, we just call it, once we get used to this, we call it just vector E dot. So in everyday language, we might just in short form call it A dot B, but the proper definition of this symbol, or what this symbol represents, is that it represents the scalar product of vector A and B. Now, how do we calculate it, or what is the definition of the operation itself? It is magnitude of the vector A multiplied by magnitude of the vector B multiplied by cos of theta, where theta is the angle between the two vectors A and B. So on the right hand side, it is, by definition, it's such a quantity where capital A represents magnitude of vector A, capital B represents magnitude of vector B, and theta is the angle between vector E and B. So again, just don't immediately worry about Q as a definition. This is the definition. When we look at applications of this in physics, you'll understand why we define it like this. Right now, you just understand that this is a new type of operation for us. We haven't seen this before. So we define this operation by this formula, that when I'm calculating the scalar product of two vectors, what I'm actually doing is I'm multiplying the magnitude of the first vector with the magnitude of the second vector with cos of the angle between them. As simple as that. So just start by writing down this definition. Okay, so I think this should be fairly self-explanatory. This is how we define the quantity. So as an example or two, let's see. For example, if I have two vectors like this, this has a magnitude of 20, let's say, and this one has a magnitude of 30, let's say, and the angle between them, let's say this angle here is 60 degrees, suppose. And we want to find out E dot B, how much that is. Okay, so we can see that it's very simple here. Magnitude of A is nothing but 30, whatever unit that is. We'll come to the units later. Magnitude of B is in whatever units it is 20, and the angle between them, according to my diagram, is 60 degrees. Okay. So therefore, what about A dot B? By formula, it is magnitude of A into magnitude of B into cosine theta. So just substitute. So it is 30 multiplied by 20 multiplied by cosine of 60 degrees. So as you can see in this case, it just becomes 30 into 20 into half. So it becomes 300. Okay. And suppose they are in the same unit. Okay. So suppose magnitude of vector is 30 units, whether that is kilometers or newtons or whatever, then this becomes square units. So E dot B becomes this much. We can put A dot B inside a bracket, it doesn't matter. We can just leave it like this also, it doesn't matter. Okay. One in the same thing. Okay. So this is the simple understanding of what is dot product. It's just a very simple definition. Magnitude of one vector multiplied by magnitude of the other vector multiplied by cosine of the angle between them. Yes, Yashmit, you got that correct. That's good. So I think this should be fairly easy for everyone. Yeah. So let us do a small operation now. A question with some more examples. So suppose now what I've done is I've taken vectors in an xy plane. So vector A is like this. So magnitude 50, and this angle is, let's say, 37 degrees. Vector B, let us say, is lying directly along the y-axis. Let me try and make vector B a little bit more clear. So vector B now, let us say, is like this, and it has a magnitude of whatever, let's say 15. And vector C, let us draw it in somewhat more arbitrary manner. So vector C is like this, where this angle is, let us say, 30 degrees, and vector C's arrow is pointing in this direction, as you can see. So vector C is not pointing like this, it's pointing like that. So, and vector C's magnitude is again something arbitrary, let's say it's 12 or something. So all the magnitudes are in the same unit, let's say. So if all three magnitudes are in some common unit, U, let us say, whatever that common unit is U, then we have to find over here magnitude of A dot B, and also, I mean, we have to find the operation A dot B, how much that is, and also B dot C. Okay. So I'd like everybody to try and get this question correct. Okay. You can refer to the previous question you like, or you can just refer to the definition of A dot B, which we have discussed. It is magnitude of A into magnitude of B into cosine of theta, where theta is the angle between the two vectors A and B. So all you have to do is apply this and figure out what angles are applicable for each of these two parts. Okay. Yes, Sania, very good. Your first part is correct. Saurabh, good. And to answer your question, no, it need not lie in a two-dimensional plane. A dot product can be applied to vectors in 3D also. But here in this particular example, all three vectors are in the xy plane. It just so happens that in our particular example, they are lying in the xy plane. Yes, Yojit, correct. Samarth, not correct. Check your answer again. Dhruv, correct. Yasmit, check your first answer again. Viraj, correct. Soham, you're correct. You're correct. Good, Saurabh, you got both of them correct. Mehak, your second one is also correct. Yes, Smith, correct. Yeah, Tush, there is no explanation of why AB cos theta again. Again, you are chasing something which there's no answer to. That is the definition of dot product. That it is AB cos theta. उसको ऐसे define ही करते हैं operation. Okay, so let us understand the first part. If you just isolate the vectors A and B over here, you will understand that our vector E was lying like this, and in comparison, our vector B was something like this. Okay. So in the question, it was given to us that this angle is 37. The angle that the vector E is making with the x-axis, that is 37. And you can see that the vector B is already lying along the y-axis. So now you see what is the angle between A and B. For the case of A and B, this angle theta is nothing but 53 degrees. Okay. And magnitude of A was given to me as 50. And magnitude of B was given to me as 15. And theta now you worked out from the diagram as 53 degrees. So by definition, A dot B is becoming how much? It is becoming AB cos theta. So it is 50 into 15 into cos of 53 degrees. And it's a matter of keeping in mind that cos 53 कितना होता है? 4/5. Okay. So that becomes 4 square units. Or you can say it is 450, whatever unit that was common, uska square. So this is becoming your answer for the first part. This is all you are expected to do in this calculation, nothing else. You are just applying the definition of dot product. Oh, sorry, it's 3/5. Yes, my mistake. But the answer will be this one, 4. 3/5 into this, as you can see, will give you 9 into 15. Correct. So I made that correction. Good. Okay. So this is the first part. Okay. Now, likewise, what you do is you repeat this operation now, but for B and C. Repeat this operation for B and C. Okay. Like we've done for A and B over here, you pick up B and C and understand the angle between them. Yes, Kevin, Devansh, and Aditya, I noted that it's 3/5. So once again, so notice that because the vector C was drawn like this, magnitude is 12 and this angle was 30 degrees, whereas vector B was lying in this sort of direction, where it's at 90 degrees to the x-axis and its magnitude was 15. So if you just draw them separately, you'll understand what is the angle between them. You'll understand that the angle between them is 60 degrees because you see here this angle is 30 degrees because this is the direction in which C was lying. This angle was 30. See this angle and this angle. So now this is 30. So now the angle between these two vectors, that is how much? That is 60 degrees. So this is the angle you will substitute for theta. So your vector C of magnitude 12 is at an angle of 60 degrees with respect to your vector B, which is of magnitude 15. Okay. So now you can see that when we define the value of B dot C, we get magnitude of B into magnitude of C into cos of theta, where in this particular case theta is 60 degrees. Okay, so substitute that, so you will get 15 into 12 into cos 60. It will again give you 90 square units. That is your B dot. Yes, very good. 90 is the correct answer. Yes. Okay, now what if we have an example like this? So I think this example should be clear to all of you. So what if we have an example like this now, where one of our vectors is parallel to the x-axis like this, and our second vector is, let us say, like this now. So let's take that same vector B we had earlier, or C or whatever. This time let's take that as B, and this is of magnitude 40, whereas our new vector E this time is along the positive x-axis and its magnitude is 50. So again we want to find out A dot B. So they are in the same unit. Yeah, Shravya, why we are not taking 120 degrees in the previous case? Again, it should be very clear to you that this vector C is pointing in this direction. See, it's pointing like this. It's like this. And this vector B is pointing in this direction. Okay, so this angle is not 120. This angle is 60. In which case it would have been 120. If vector was pointing like this, and vector B was pointing this. ऐसा अगर होता तो then this angle would have been 120. But it's not this case. No? It's in fact this case. You can see the arrowhead of C. It is pointing in the direction. Okay. So your so coming back here, in this we will get a negative quantity. Okay, we'll see here that in this particular case, what is the angle between A and B? The angle is in fact 120. Sorry, 150. To draw B from a common base, just bring the two vectors to the same origin. You will see that this angle is 30, which means that the angle theta between them is how much? It is 150 degrees. So A dot B which is EB cos theta into cos 120, sorry, 150. Okay. So you'll see that cos 150, remember, is a negative quantity. Cos 150 is minus of cos 30, which is minus root 3 by 2. So this will become 2000 into minus root 3 by 2, or minus of 1000, or we can write it approximately as units square. Okay. So this is becoming our A dot B. So this example shows us something interesting, that A dot B can also be a negative quantity, or the dot product or the scalar product of A and B can result in a negative quantity also. Yes, Tanish, that is correct. Good. Yudit, Sanya, Yasmith, all of you got the correct answers. Okay, Nityashi, Stavya, Dhruv, of course, you also got it correct. Okay. So this also shows us something interesting about the dot product, that observed degrees. A dot becomes the scalar product of two vectors can also be 0. And if theta is obtuse, then A dot B is in fact a negative quantity. So I'll just first take you through the working of the previous question. We'll come back to that property. I'm just using an approximate value of root. So this is also equally correct. Read the answer this way, there's nothing wrong. You don't have to go to this step. Okay. Right. So now that we have understood the simple definition, and there's nothing difficult in it, as you can see, now we come to properties of dot product. Okay. So you've seen the definition. Next thing we see is properties. But to understand the properties, first let us just rewrite the definition. So dot product of two vectors A and B is AB constant. Okay. So the first and foremost property that we should see is that scalar or dot product of two vectors A and B, for example, gives a scalar quantity. So if you think about it, this is the first type of operation we've learned where this happens. Now the output of my operation gives us what kind of quantity? It gives us a scalar quantity. So think about it, no other operation we have studied till date has this thing. If you're adding two vectors, the resultant, it's a vector quantity you get. If you subtract two vectors, it's a vector quantity that you get. If you multiply a vector with a scalar, you get a vector quantity. But here you can, what is on right hand, it is magnitude into cos of an angle. So it's nothing but the product of three scalars. Okay? So this is as per the definition. You can see that is because you can see the right hand side, the formula, it is mod A into mod B into cos theta. So this is the product or the multiplication of three scalars. In fact, that is why the name given to it is scalar product, because the resultant of this operation is a scalar quantity. Okay, so the name dot product comes the fact that the symbol used for it is a dot, and also the alternate name scalar product comes in because the resultant operation gives us a scalar quantity. Okay, so that's the first thing you can see from the definition itself over here of scalar product. Piyush, you can re-log in if there's some problem with your audio. Yeah, Piyush, I've just explained that point and I've written it down over here also, because the scalar dot product of two vectors gives us a scalar quantity. It does not give us a vector quantity, it gives us a scalar quantity. That is why it is called a scalar product. Now, the second thing you can see over here that A dot B is equal to B dot A. Okay. That means it is a commutative type of operation. And that again you can see in the definition itself. B dot A is nothing but magnitude of B into magnitude of A into cos theta. Aditya, negative doesn't mean it has to be a vector quantity. The x coordinate of a particle is a negative quantity. That doesn't mean that it's a vector. For example, in physics, electric charge can be both positive and negative, but charge is not a vector quantity, it is a scalar quantity. So negative sign does not indicate that it's a vector quantity. Now the third property is something that we've already discussed. If theta is equal to 90 degrees, then E dot B becomes 0. If theta is acute, then E dot B is a positive quantity. And if theta is obtuse, then E dot B is a negative quantity. Yeah, commutative operation is of this type that, for example, addition is commutative because A plus B is equal to B plus A. 2 plus 3 is equal to 3 plus 2. So addition is commutative. But for example, subtraction is not commutative. A minus B is not equal to B minus A. 5 minus 2 is not equal to 2 minus 5. So that is a non-commutative operation. So a commutative operation is one where if you interchange the two variables that you are operating, it makes no difference to the result. Now the fourth property is going to be very important, is that dot product of A with the sum of two vectors can be expanded as the dot product of A with B plus the dot product of A with C. And this is called the distributive property. So this particular operation we are dealing with, which is called the dot product or scalar product, it has these two important algebraic properties. One is that it is commutative, that is A dot B is equal to B dot A, and the other is that it is distributive. So A dot of B plus C is nothing but A dot B plus A dot C. Okay. So I'll just take you through the properties so far once more. And all of them, the reason for the property lies in the definition itself. Because we have defined the operation A dot B by this formula, that it is magnitude of A into magnitude of B into cos theta. So you can see that right hand side of it, the formula, it is the product of a magnitude into another magnitude into another number. Cos theta is not a vector quantity. It can be a positive or negative quantity, but it's just a number. So the product of three scalar things has to be a scalar. So that is why we can see that the operation of dot product applied on two vectors gives us what kind of quantity? It gives us a scalar quantity. And that is why it is called a scalar operation. Okay. Then the next thing you can see is that if I just interchange B and A over here, instead of A dot B, in the definition I put B dot A, I get B into A into cos of the same angle. So ultimately you can see that is the same thing. Whether I write AB cos theta or BA cos theta is one and the same thing. So that is why from the nature of the definition itself, we can see that the dot product is a commutative kind of operation. Okay. And the third thing is based on the value of cos theta, which we discussed earlier also. Cos 90 is 0. So whenever we have perpendicular vectors, their dot product becomes 0. Acute angle gives you cos of a positive quantity, first quadrant. So that is why if the angle is acute, the scalar product results in a positive quantity. Obtuse angle, second quadrant cos is negative, as you know. So that is why A dot B becomes negative. Okay. And final fourth property is that it is distributive in nature, that A dot B plus C is equal to A dot B plus A dot C. This is also fairly obvious because it just applies from the definition. And one more important property from here is that if you take dot product of a vector with itself, it just becomes square of the magnitude. Okay. Because cos 0 is unity. So it will become A into A into cos 0. So that is nothing but magnitude of A square. It is equal to BA cos theta. Please pay attention to what I'm saying. Distributive, I have not said that it's not commutative. Pay attention over here. I'm saying it is a commutative type of operation. So A dot B is equal to B dot A. Okay. So yeah, a couple of people have got logged out and just re-logged in. So for your benefit, I'm just repeating the properties we have written so far. Tanish, the audio is all right from my end. I am monitoring the internet connection and the audio. So might be your connectivity is giving you some difficulty right now. So you can try and reconnect if you want, or you can see the video lecture later. It will have proper audio. Okay, so the new property that we have written, dot product of a vector with itself is nothing but square of its magnitude. So again, apply the definition. A dot B is A dot A current. So it is what magnitude of A into magnitude of A itself into the angle between A with respect to itself. That is how much 0. And cos 0, is unity. So it becomes A square. Okay. So that is why, in fact, we have another important property that from this, we understand that if we take dot product of I cap with I cap, it gives us 1. Dot product of j cap with j cap, it gives us 1, because not only we are taking with self, but we are also taking unit vector. So it will become A square, but for I cap and j cap, what is their own magnitude? It's unity. So it's 1 square. So it becomes like that. So similarly, k cap's dot product with itself is 1. However, if you take dot product of one unit vector with another unit vector, not self, but I with j, they are at 90 degrees, so it should be 0. Similarly, I dot k should be 0. Okay. and similarly j dot k should be 0. So about unit vectors, this is what we remember about the standard unit vectors. Any unit vectors dot product with itself gives you 1, whereas any unit vector dot product with another perpendicular unit vector gives you 0, because cos 90 is 0. No, we cannot take dot product of 3 quantities. It has to be of 2 quantities better. Okay. So now, with this property in mind, for example, we can develop a formula, the final one. Dot product in component form. How do we calculate dot product in component form? So let's start with a couple of examples, then we'll develop a general formula. Suppose I have a vector A, which is something, let's say 2i cap, and I have a vector B, which is, let's say, something 5i cap plus 3j cap. And now I want to calculate A dot B. So I know that in terms of formula, it is AB cos theta, but now I don't know directly A, I don't know directly B, I don't know theta. So instead what I'll do is I will use, yes, the answer is correct, Kevin. What I will use is, I'll use the distributive property. Okay, so what I'll do here is, I will substitute as A as its value in component form. So that's 2i cap. Dot product with B as its value in component form, which is 5i cap plus 3j cap. The next what I'll do here is I'll use the distributive property, that dot product of a vector with the sum of 2 other vectors becomes A dot B plus A dot C. So I'll use this property over here. Okay. So using this over here, as you can see, it will become 2i cap dot product with 5i cap plus 2i cap dot product with 3j cap. Okay. So next step, we can write this as 10 into I cap dot I cap. Now from previous slide, we know that this is 10. I cap dot I cap is unity, but the other number we have 6 over here is with I cap dot j cap. Now we know I cap dot j cap is how much? 0. So this becomes just 10. Okay. Because we know that dot product of any unit vector with itself is unity. Okay. But dot product of any vector with a perpendicular unit vector is 0. So we are just using that property over here. So we are using a combination of the distributive property and that's how it is. So A dot B becomes. So this is just a numerical example to show how using the table of properties that we have for dot product, we can work out a simple dot product operation when the vectors are given in component form. But obviously this will become very lengthy if we apply it to 3 dimensions. So we will develop a sort of formula which we can directly apply when vectors are given in 3-dimensional component form. So we don't have to open up and use so much algebra and all that. All these steps will not be necessary. But first make a note of this, please. This was just a simple formula to, why it is 0, I explained earlier, because they are perpendicular to each other. I cap and j cap, the angle between them is 90. So that's why. Okay, so let's develop a general formula now. component form. So suppose we have three-dimensional vectors. E is equal to Ax, Ay, and Az. Three components. Okay. And similarly, my vector B is also known in three-dimensional component form. I want to calculate A dot B. So when I do this operation, so if you were to open this bracket and apply distributive property, you would get 3 into 3, 9 terms. Okay. But you can see in those 9 terms, all the terms having I dot j will be 0. All the terms having j dot k will be 0. All the terms having I dot k will be 0. Whereas all the terms having I dot I unity, j dot j unity, and k dot k is unity. So now just visualize this step. When you open this with those 9 terms, which of them are having I cap with I cap and j cap with j cap like that? It is nothing but the product of Ax I cap with Bx I cap by dot method. So that is just becoming Ax into Bx, and I cap dot I cap is 1. So that is multiplied by 1. Whereas now you see Ax I cap dot By j cap will give you 0 because I dot j is 0. Similarly, Ax I cap dot product with the third term, k cap term will give you 0. So with Ax I cap, only one term survives, which is which one? The Ax into Bx. Similarly with Ay, the second term, now you will have j cap dot I cap with Bx, that is 0. But j cap dot j cap is unity. So the second term will just become Ay By. And the third term of that will again become 0. And similarly with Ez k cap, the dot product with this term, I cap term will be 0. The dot product with this term, j cap term will be 0. And only the third term will survive, which is Ez, Bz. So this becomes our general formula. So from this point onwards, we don't have to do so much. We have to just directly apply this formula when the vectors are given in component form. Whereas if the vectors are given in geometrical form, then we use that other definition that it is AB cos theta. So you can just see if we just compare with this side note that I shown you, you understand that when you open this bracket by distributive property method, your first term of this row, that is Ax I cap dot first of this one, Bx I cap, is resulting into Ax into Bx because I dot I is 1. But your second term, Ax I cap dot By j cap, that is resulting in 0 because I cap dot j cap is 0. Similarly, the third is becoming 0. Similarly, when you take this term, Ay j cap, and take dot product with each of these, you can see the first and third will give 0, but the second term Ay By will come with unity because j cap dot j cap is 1. Okay. So for example, if I have any given vector now like this, is let us say 2I cap plus j cap minus k cap, and B let us say is I cap plus 2j cap plus k cap. And I ask you what is A dot B. Now the answer to that is very simple. A dot B is Ax into Bx, so that is 2 into 1, plus Ay into By, so that is 1 into 2, plus Az into Bz, so that is minus 1 into 1. So further, this becomes 2 plus 2 minus 1. So that in fact becomes 3. Correct, yes. So that is the correct answer. Okay. So as I told you that from now on, there's nothing very difficult left in vectors in terms of calculations and all. It is just more or less, direct application. But yes, the two new operations that we'll be learning, one we have done today, which is scalar product, and one we'll do in the next lecture, which is vector product or cross product. They are defined in this manner. Okay, understood this, people? So let's do a quick example based on all these properties and method and all that we learned. So properties are done. There are these 6 properties that we have to discuss. So next example. Okay, so let us say we have all these vectors given to us. So find A dot B and A dot C, and also find this, okay, by using the definition that A dot B is PB cos theta, and alternately again do the recalculation of these and show that your calculations are correct by using component formula for dot product. Okay. So do it by both the methods and verify for yourself that what you're getting is correct by each of the methods. Okay. So try this out, people. Yeah, Yasmin, to answer your question, there is no particular diagram which gives us dot product, because a diagram might give you the magnitude of the vectors and the directions, okay, like that, but it's not going to give you the dot product itself. So just try to get both these parts correct by both the methods, by method A as well as method B. If you can do that, then you have no difficulty in scalar product from this point onwards. Okay, so let me just verify the answers. And a lot of people have got the correct answers. Okay. So not to worry about that too much. So let's first go by the geometrical method. If you go by geometry, you will realize that your vectors E and B actually happen to be perpendicular to each other. I may have got the colors reverse, it doesn't really matter. So क्या हो रहा था यहाँ पे that with respect to my x-axis, you could see that this angle was 37 and this angle was 53. So that also meant that this angle is 90. So as far as A and B is concerned, they are perpendicular vectors. His magnitude was whatever, 15, 12 and 10. So 15, 12 and 10. Okay. But now, so for example, I want to calculate E dot B. That is just becoming AB cos 90 degrees. So that's 0. Because you can see the angle between A and B. Okay. You want to calculate E dot C. You can see that will become AC cos of 127 degrees. Because you can see that this angle here this angle will become 90 plus 37 or 127. So now you can see, so that will become the value, it will become mod of A is given to me as 15, mod of C is given to me as 10, and cos 127 I can write as minus cos 53, which I can write as minus 3 by 5. So it's 15 into 10 into minus 3 by 5. So that is becoming how much now? Minus 90. Okay. So E dot C becoming minus 90. And E dot B was 0. So this is the first part done geometrically. And the second part, we can just use the distributive property. So that is nothing but E dot B plus E dot C. And then just copy paste the values from here. Nothing else is required. You can see A dot B was 0 and this was minus 90. That's minus 90. So as you can see, there's nothing difficult. It is just following the definition and the formulae just systematically. Nothing more to this. Okay, so many of you got this correct. Mehak, Yasmith, okay. Kevin, Aditya made some mistake, but it's okay. Sanya, all of you got this correct. Dhruv, Soham, you've written it correctly. You have to just solve the whole thing. Okay. Now let's also do this by component method. So we go by component method. You'll have to first write A, B, and C in component form. So the vector E, you can see, was making an angle of 37 degrees with the x-axis and its magnitude was 15. So it will become x component will be e cos theta. So that is 15 into cos 53, which is 4 by 5. So that is 12. Okay. And y component will be similarly e sin theta, which when you calculate will become 9. So this vector in component form is 12 I cap plus 9. Now similarly, if you see the vector b was, let's say something like this. Its magnitude was 12 and this angle here was 53 degrees. So the angle it made with the x-axis was 127 degrees. So for the vector b, you can see the x component is 12 cos 153 degrees. Okay, so that is becoming minus 12 into 3 by 5. So minus 7.2. And the y component 12 sine 153. Sorry, 127, not 153. So it will become plus 9.6. So the vector b will come out to be minus 7.2 I cap plus 9.6. And similarly, the vector c, you can see is very easy. It was directly pointing downwards. So the vector c was just like this, downwards, and of magnitude 10. So the vector c can be just written as minus 10. So now we can see that E dot B will be 12 into minus 7.2 plus 9 into 9.6. So when you work this out, you can see this will come out to be 0. And E dot C will be 12 into 0 plus 9 into minus 10. So that is minus 9. That's also what we got earlier. Okay. And E dot B plus C, you can do by the same method only. You can just open this. Or if you like, you can first calculate this also. You can also do it this way, that this is 12 I cap plus 9 j cap dot product with, now just do B plus C. So B plus C over here you can see will become 12 I cap minus j cap. Sorry, B plus C. So on that we are adding this and this. So it will be minus 7.2 I cap. Okay. Plus this, so that is minus 0.4 j cap. And now when you do this dot product, so that is equal to 12 into minus 7.2 plus 9 into minus 0.4. So when you work this out numerically, you will see this will also come out minus 9. So I mean, nothing really there. It's just matter of substitution and doing the algebra. Oh, thanks for informing me. I have got them in. Yeah, thanks for informing me. I have got the people back from the meeting room. Service. So hope this is clear now. Okay. So if you just revise through these examples we've done in class today, and then there will be a worksheet for you which I'll send this week, which will have dot product. So you should not have too much difficulty with this. Now, one last thing we'll see from dot product is that, remember I told you many times that there will be an alternate way of calculating the angle between two vectors when they are given in component form, rather than what we had seen earlier by drawing the two vectors and all that. And that day has come today when we learn that alternate method of calculating the angle between two vectors. Okay? So we'll see calculation of the angle theta between two vectors, let's say A and B, which are given in component form. Okay. By dot product method. Okay, so this is a very simple thing. We know that A dot B is equal to AB cos theta. Okay. So the inverse of this is that cos theta is E dot B divided by product of the magnitudes. So from this we can find that theta is so-called cos inverse. But don't get into complicated inverse trigonometry formula and all that. Okay, just understand that we use that simple method that if I know the value of cos theta, from that I can directly predict the value of theta. So it's very simple. So for example, suppose my vector E is, let's say, 3 I cap plus 3 j cap. Okay? And let's start with something simple. The vector B is, let's say, just 2 I cap. Now how much is theta? Now see, the example is so simple that you should be able to predict it anyway without even doing dot product. Vector A के क्या हो रहे हैं? दोनों components equal हैं and दोनों positive हैं. So it's making an angle 45 degrees with the x-axis. It's pretty obvious, you know? Whereas the vector B is lying along the x-axis. So what should be the angle theta? You know it should be 45 degrees. You know? It's pretty obvious without even doing anything. But let's just check. So check. So cos theta should be equal to A dot B divided by mod A into mod B. Okay. So now from these vectors, let's first calculate A dot B. So A dot B कितना है यहाँ पे? AX into BX, that is 6, plus AY into BY, that is 0. So it is 6. A dot B is 6. What about mod A? It is square root of 3 square plus 3 square. So it is 3 root 2. And what about mod B? It is 2. Okay. So therefore, now substitute these back over here. So substitute these here. And you will get cos theta as A dot B is how much? It is 6. Magnitude of A was 3 root 2. And the magnitude of B was 2. As you can see, cos theta is 1 by root 2. Okay. So in proper language of trigonometry, we can say that theta is cos inverse of 1 by root 2. But this last step is unnecessary. You can directly see that cos theta is 1 by root 2. You know that theta is 45 degrees, or that's it. So to begin with, I have taken a very simple example so that you can understand that this is giving us the correct result. But now even if we have something which is more complicated, like in 3D, we can find it out easily. Let's look at another example. Vector A is suppose 2 root 3 I cap plus 2 j cap, and vector B is minus root 3 I cap plus j cap. Now we ask find the angle theta between the vectors A and B. So just apply the same method as the previous question and work this out quickly. Tell me how much you should get over here. Just apply the same method that I've done over here, this method. No, it's not the sense in, that is by definition. You know, if we say that cos theta is equal to x, so by definition it means that theta is cos inverse of x. This is the definition of cos inverse function. So for example, if we know that cos of 30 degrees is root 3 by 2, is a known fact, then we also know that 30 degrees is cos inverse of root 3 by 2. Or, you know, if you're speaking about proper mathematics, you should actually express 30 degrees in pi. So this is pi by 6 is equal to cos inverse root 3 by 2. So this is just about the definition of inverse trigonometric functions in mathematics. Yes, Tanish, very good. Correct. Mehak, correct. Dhruv and Samar, check your answer. Sania, correct. Dhruv, you had got the answer right. Now, again, second time, I don't know why you gave the wrong answer. Yeah. So let's apply the same method that I applied above over here. So मैं क्या करूँगा यहाँ पे? You don't need to memorize anything. Just know the definition. So since A dot B by definition is AB cos theta, so I can apply the inverse of this one because the two vectors are given in component form. So it's easy to find out A dot B. It's easy to find out mod A. It's easy to find out mod B. The question is how much is cos theta. So cos theta should be A dot B divided by mod A into mod B. Okay. So I should be able to find this out. Okay. Now from the two given vectors, tell me what is A dot B. A dot B कैसे निकालते हैं? AX into BX plus AY into BY. That is because they are two dimensional here. So the Z components are 0. So otherwise there would be AZ plus AZ BZ also. So that is how much over here. AX into BX will become minus 6. Okay. AY into BY is plus 2. So their dot product's value is how much? Minus 4. So immediately you can understand one thing, that they are making an obtuse angle because the dot product is coming as negative. So this we will substitute over here. Then similarly, what is mod A? Mod A is root of AX square plus AY square. So from that you can see it is 4. Mod A is 4. And mod B similarly is root of BX square plus BY square. So that is becoming how much? That is becoming 2. Okay. So these two values also now we will substitute in the denominator. Just substitute these here. So substitute this thing and these two things over here. So we are getting cos theta as how much? A dot B, which is minus 4 divided by mod A, which was how much? 4, and mod B, which was 2. So cos theta is coming minus half. So you know that theta is 120 degrees because you know that cos 60 is half. Therefore, cos 180 minus 60 is minus half. So from that you know. So very simple really, nothing difficult in this. Okay. Okay people, so with that we conclude today's lecture, which was about this section, dot product, and also the early part about direction cosines, okay, and the relationship between the direction and cosines. Okay, so hope everything is clear here. Make sure you do a revision of today's lecture. But as I said, it's actually one of the easier part of vectors. Okay. You should not have any difficulty at all once you attempt a few questions based on the formula and all you've done. And I'll be sending you an exercise. But now you can also start, going through all these sections in a detailed manner from your module, your physics module, which is useful mathematical tools in physics. That particular module. Okay. Yeah, projection also will be understanding. Okay. All right, people. So that's it for today's lecture. Thanks.